my dear students. So now I'll be showing you the entire reinforcement, how it has been completed, and then you'll understand the logic behind all these things. Right now you can see it here. All the work has been finished. Like I mentioned, you see in the distribution still, one bar at the top, one at the bottom, one at the top, one at the bottom, top, bottom. Right, in this way we have done all the arrangement. And also if you observe the beam, you can see the top extra reinforcement and all. Right, yeah. Yeah, now I'll start with the logic now. Yeah, so the typical behavior of a slab is something like this. Okay, I'll start in this way. So this is a one panel for me, this is panel number 2. So whenever the load comes on the slab is going to behave something like this. I'll start with this. So here again I'll get a negative bending moment, I'll get a positive bending moment, I'll be getting a huge negative bending moment here, I'll be getting a positive bending moment, I'll be getting a negative bending moment. So if I try to put one straight line to differentiate that, so let us say this is my one straight line, right? So whatever is above the straight line, that is this part and this part, it is a negative bending moment. That means your slab will try to lift up in this portion. Wherever I have shown the line below the red line, that is this part, this is my sagging bending moment. That means in this particular portion my slab is going to sag, that is going to come down. Okay, similarly here also, right? So I hope this much concepts are clear. So now this is the overall slab I have explained, but I'll take it out and I'll explain you for only one particular slab, and we'll try to understand that in a better way. Yeah, so here what will happen, this is my negative bending moment, this is my positive bending moment, and from here again negative bending moment will happen. So I'll change that with a different color. So this negative, I'll go with this yellow color. Yeah, this is negative. Okay, again from here also again negative is going to happen. Okay, and this is my positive, the one which is pink in color is my positive. Now since my slab was trying to lift up, what I should have done, I should have provided the top reinforcement, right? Because even in the beam also we did the same thing. If your beam was trying to lift up, we wanted to provide the top reinforcement. So that is why what we have done, we had provided the bar straight, you remember, up to here we have provided the bottom steel, right, up to here. But since from this point my slab was trying to lift up, what I did, for the same bar I gave a crank. Crank is nothing but a bend, and I have taken the bar to the top. Getting my point? Similarly, this was my cutoff point. From here my slab was trying to lift up, right? You can see this bending moment diagram. If you want to put it in a clear way, let me do in this way, so that we don't have any confusions left after this. Yeah, I'll take this as my cutoff point. So this is my cutoff point, okay, where my bending moment is changing the sign, and similarly this is also my cutoff point where my bending moment is changing the sign. Now we are in a better position to understand that. Yeah, great, right? So again this was my green. Here the bending moment is changing from which, positive to negative. Again I have done the cranking of a bar, I gave a bar crank and I taken to the top. Got it? So this is the logic behind that, right? Now with this explanation we'll continue. So my slab was trying to lift up, so I'm giving a crank bar here, that is I'm giving a top reinforcement. So in the bottom my slab was trying to come down, that is it was a sagging bending moment. So since it was a sagging bending moment, I don't require a top steel, I have to provide a bottom steel. That is why you can see here we have provided the steel only in the bottom. Got it? So this is the main idea behind that. In the same way, these are your distribution steel, which we are given from temperature and shrinkage point of view. The main agenda was something like this. So that is why we have taken the bar to the top on either side, and this is my bottom reinforcement. This much is understood? Yeah. So next question is that, why is that only in this portion my slab is trying to lift up? Why is that my slab is trying to lift up here? We'll try to address that question, right? So the reason behind that is, wherever we have a slab and a beam intersection, that means, see, I have a beam here. Do you agree with me? Yeah. So I have a beam here and I have a beam here, and where I have a slab, so I have a slab here, right? I mean this entire portion is a slab, but where is the intersection more? So this is beam and this is slab connection, this is beam and this is slab connection. So wherever we have this beam and slab connection, no, so that connection is actually that is a simply supported connection. Right here it is actually a simply supported, simply supported connection. Actually it is a simply supported connection where it is here, okay, not here. This is not a simply supported connection because here we have continuous slab, especially at this particular zone, because if I have a beam here, next to the beam I don't have any slab, so this is actually a simply supported connection, okay. So according to the textbook language it is a simply supported connection, but practically what will happen, once you pour the concrete, there will be a bond between this beam and the slab. In the same way, once you pour the concrete, there will be a bond between this beam and a slab. So since there is a bond between them, what will happen, a connection gets developed, and that connection, whatever practically developed, it is called as a fixed support. It is called as a fixed connection, okay, or a fixed support, or a fixed connection is a good term to use. So whenever we have a fixed connection in this way, why the fixed connection gets generated? Because there is a bond. There is a bond between the steel and also aggregate. So in this particular region it becomes a fixed connection, and when the load comes, then what will happen? Obviously my beam will try to lift up. I mean my entire this much portion will try to lift up, but in the middle portion it will try to go down, and here it will try to lift up. So that is why the code says that you have to provide a top reinforcement on both the side. Got it? So that is the main idea behind this slab reinforcement, and that is why practically when we detail anything, no, so this is a kind of detailing what we try to give. We can see the crank bar given here, right? So this is my crank bar, you give it L by 4 distance. Now one more point we need to understand. It has been found that this whatever negative bending moment happens, no, it will happen at a distance of L by 4 from the this negative bending moment. What happens from here, it is sagging, again from here negative, right? So whatever negative is happening, let me quickly draw that. From here to here this is negative bending moment, from here to here whatever is negative bending moment. So till what point this is negative bending moment? So according to the code book it says that up to L by 4, whatever is your span you divide it by 4, up to that this the effect of negative bending moment will be there, and after that it is a positive bending moment. Got it? So that is why we try to give the crank bar up to a length of L by 4. Now next is that, so again the next is that we have to understand one more thing, that is, you see here this whatever steel you have provided, right, this steel whatever you have provided, here the spacing is how much? Here the spacing is, let us say it was 100 mm, it was 150 mm center to center spacing. So this spacing, right? So I'll write here quickly. See, few things will take you time. If you are a new learner, it will take some time, but it is very good way that you are learning, okay. So this was the spacing, how much? I'll write it here quickly. It was a 6-inch spacing. 6 inches means it comes out to be 150 mm center to center spacing in the center. But the same thing can you observe at the sides? In the sides I'll do in this way. See, here your bar is not continuing, whereas here your bar is continuing. Here your bar is continuing, right? But again next you don't have the bar continuing because that bar has been cranked, but this bar is going straight. Getting my point? Next this bar has been cranked, whereas this bar is continued, right? So what has happened now? Whatever spacing we were giving of 6 inches 150 center to center spacing, near the support the spacing has got doubled. You agree with me? If I try to clear everything, let me put it in a better way. See here, for this bar my bottom steel is there, good. Next my bottom steel is here, 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 right? But if I see the same thing in the middle portion, if I do that, I'll do it for the middle portion. See, in the middle portion the spacing is very close. That means it is a 6-inch center to center spacing what I have kept. But by the time I reach to the sides, I'll do it on the right side as well, so that we'll be in a position to understand in a more better way. Quickly I'll take another 2 minutes. We have this bottom steel, we don't have here. Here bottom steel is continued, here bottom steel is continued, here bottom steel is continued, here bottom steel is continued. Good, got it? Now you see here this spacing is little less, right? This is my 6 inches spacing. I'll write here it is my 6 inches, or I'll write this as 150 mm spacing. But what has happened to the sides part? What is this spacing now? Because this spacing has got doubled, right? Do you agree with me? This spacing is doubled. Now instead of 6 inches it became 12 inches, 12 inches, 12 inches and 12 inches. Same here also it is 12 inches, 12 inches, 12 inches or 300 mm, one and the same. I'll write here it is 300 mm, here it is 300 mm. So why is that so? We have done such thing. The reason behind this is actually if I try to plot the bending moment of this, I'll try, see everything is related to bending moment and shear force. Entire civil engineering is all about bending moment and shear force. If you understand that, you become a good engineer. If you don't know that, throughout your life you will be in a confusion. Okay, so you see this bending moment. See, so what is this bending moment happening, you tell me? So if I try to put one line here, again I'll put one cross section line. Yeah, yeah, I'll put this line in this way. I'll put a line here. Okay, yeah, great. Similarly, let me make this line a bit fatter. This one, yeah, great, good. So now understand. See, this, here I have a maximum bending. You can see from this white to this white intersection, you see I have a maximum bending moment here, right? Here beam is trying to sag a lot. So since my sagging bending moment is more, I require more steel. And how can I provide more steel? We know that more steel can be provided by providing at a lesser spacing. That is why you can see the spacing in the middle everywhere. It is 6 inches, 6 inches, 6 inches, 6 inches and 6 inches. Now from this white color intersection to the support, that is up to here, see your bending moment is very less, right? See, if it here, from here it is going on decreasing, 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 and it is almost zero here. In the same way, if you see here, from here again it is decreasing, 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 almost it is zero, right? So maximum bending moment was only from this region to this region. Beyond this point and beyond this point, your bending moment is very less. So up to here your bending moment is zero. That means you don't require any steel. So what we'll do, instead of not giving any steel, we'll try to reduce the spacing. In the same way, from here to here we'll try to reduce the spacing. So that is why what we do, 6 inches center to center spacing will give in the middle, and at the sides we require very less. The bending moment itself is very less. When the bending moment itself is very less amount of steel is required, and less amount of steel can be provided by increasing the spacing. So what we do, instead of that we increase the spacing. That means we double the spacing. So it was 6 inches or 150 mm. At this corner, I mean at the ends, it will be 300, 300, 300, 300. Similarly it is 300, 300, 300, 300. Okay, you got the idea? So this was all about the bottom steel I am speaking of, right? So in the same way, I'll delete everything now, right? You got an idea, no? So that is my bottom. Now coming to the top steel, you know. So in the top steel, what we have done, in top steel we had a negative bending moment. So what we did, whatever yeah, one more point I want to clear. See, so that is why what we did, since the bending moment itself is less near the support, I'll put one line. So yeah, so this was my cutoff point and this was my cutoff point. Yeah, so after this point my bending moment was very less. After this point my bending moment was very less, right? So what I did, I gave one bar straight. I'll start from here. I gave one bar straight, and after that I gave another bar straight. But the remaining bar I did not cut. Instead of cutting, what I did, no, I took the same bar and I did a crank of that. I did a crank bar in this. So I did a crank bar in this. Got it? Again, next bar I gave straight. That is a black color, you can see, no. Next bar again I gave straight. After that again the next bar whatever I have given, no, I will give it straight up to this length, because here my sagging bending moment is more. And after that I'll do the cranking of the bar, because I require because there was a hogging bending moment and because there was a hogging bending moment. Got it? So I'll crank the bar. Got it? So this is the main idea behind that. Now whatever negative bending moment you have given, no, there actually the steel requirement was more only. That means here by doing a crank bar, what has happened, the spacing between this, I'll tell you one more thing. Okay, this spacing, what has happened, actually this spacing you should keep, this spacing also you should keep at 150 center to center spacing. Okay, the distance between the crank bar has to be 150 center to center spacing. But practically what has happened now, since the spacing is double, this is not 150, this is 300, right? Similarly this is also 300. You are getting my point? Similarly this is also 300. Similar, this is also 300. Here also it's the same thing. I wanted the spacing in the crank bar to be 150, but it has gone to 300, 300, 300. So in order to keep the spacing 150, now we are going to give one more steel, that is called as top extra bar. Top extra bar. And in the, yeah, it is called as top extra bar. Got it? So in the next video, after this I'll be playing one more video. In that we'll be able to see how the top extra bar is provided. And why the top extra bar is provided? Because the crank distance should have been 150, but since we had taken one bar crank, we had taken alternate bar crank, I'm falling short of that distance. Okay, this distance has doubled now, so I want to bring it down. So I'll give you idea here itself. So I'm going to place one more bar in between this. I'll show that in between these two crank bar, no, I'll be placing one more bar. In between these two crank bar, I'll be placing one more bar. In between these two crank bar, I'll be placing one more bar from both the side. Here also I'm going to do the same thing. Here also I'm going to do the same thing. Here also I'm going to do the same. Throughout, everywhere we are going to do the same thing. And where is the reference for that? The reference for that is, I'll go to the structural drawing, and you can see here something they have mentioned here. What is this? You can see here. You can see here this bar. And what is the distance mentioned? It is L/3. So this bar, whatever they have mentioned here, that is called as your top extra bar. Similarly here also you can see, no, they have mentioned something. It is L/3. That is from here to here. It is L/3. You can see this L/3. So that is that bar which we need to provide in between the two crank bar. Okay. So now first we'll try to see this entire layout, and then I'll show you that image. I mean that particular video where the extra bar will be provided. So first see all the thing. Now try to apply the logic whatever I explained. Try to see the slab in that manner so that you get an idea. Okay. Yeah. If I pause it here, and if I ask you to plot a bending moment diagram, now you should be in a position to plot a bending moment diagram. So you should tell, sir, this is how the bending moment happens. We had a negative, we had a negative, we had a positive, we had a negative, positive and negative. So that is why based on that only you can see the steel here. Here we have cranked the bar because we have taken the bar to the top. We have provided a bottom steel, that is a sagging bending moment, again negative, sagging and again negative. Got it? Yeah, so you can have an idea regarding how it is done completely. Okay, I'll go a bit forward. So in this way most of the things are done. I'll be showing you one more video along with this so that we can see the entire slab reinforcement, how it has been done, along with the electrical work also done. Okay, electrical work I'll be taking a bit later, but now when I show you the slab, even the electrical work will be done, but we'll be taking up that electrical work in the upcoming lectures. So I'll go a bit forward. So here you can see all the things have been done. So I want to tell one more thing. Now if I stop it here, see, this is my cantilever portion. Okay, so this is my cantilever portion. So in the cantilever portion what will happen, I need to provide the top steel. So top steel I'm going to provide in this direction. So in the same video I'll show you again. So I'm going to provide a reinforcement here, so that will be my cantilever steel. And why it has to be provided in the top, we'll try to see the reason behind that. Here also it is a cantilever, I'm going to provide it in this way. So this will be my cantilever portion in this way, right? So we'll see this entire thing once, and then we'll come to the cantilever portion and the top extra bar. As of now you cannot see any top extra here in between the two crank. In the next video I'll be showing all those things. So up to here I hope you have understood most of the concept. What is a concept, how we need to apply and all. And one more thing I want to make it clear. So right now whatever slab we are seeing, it is all is one way slab. Suppose if it was a two-way slab, then what would have happened? Even from here also we would have got a crank bar. Your bar would have come here, it would have got crank, it would have come here. Similarly, next bar would have been your straight bar, okay, and after that again the next bar would have been your crank bar. Got it? So if you do the crank on all the four sides, then it would be your two-way slab. Right now it is only one-way slab because we are cranking only on this direction and this direction, whereas in this direction your bar is going straight, it is not cranked, so it is a one-way slab. So I hope you have enjoyed the lecture up to here. In the next lecture we'll try to see the top extra and the cantilever portion, how the reinforcement has to be given. We'll see you back in the next lecture. Thank you.